Hello everyone. In today's session, we will talk briefly about time series concepts. Anyone who is looking for a quick brush up of the concepts may benefit from this video. So I'll start with Gauss-Markov's assumption, move on to stationarity, talk about few models like autoregressive model, moving average model, ARIMA, and other known processes like Arch and Garch. Towards the end, we will also see the problem of heteroskedasticity and autocorrelation. So let's get started. In econometrics, Gauss-Markov theorem states that OLS, that is ordinary least square estimators, are the best linear unbiased estimator. In short, blue. If certain assumptions are met, here we have 6 assumptions in time series. In order to understand all these assumptions, let's consider a static model. For that, I will use this paint to write the model here. So let's say if our model is yt is equal to beta naught plus beta 1 z1 plus beta 2 z2 plus some error term. So this is a static model. Now we will look at all the assumptions. The first assumption says parameters need to be linear. Here parameters are beta naught, beta 1 and beta 2. These parameters need to be linear. It doesn't apply any condition on how z1, z2 can be. They can be log, they can be quadratic. So they are not expected to be linear, rather the parameters are. The second assumption talks about no perfect collinearity. Yeah. It means that independent variables z1 and z2, it cannot be constant, or these independent variables cannot be a function of, a linear combination of the others. The third condition is rather a strict condition, assumption of zero conditional mean. What does this assumption say? We call it strict exogeneity assumption. So this assumption says that errors in each time period is uncorrelated with all independent variable across all time period. So that's the condition of all time period makes it really strict and unrealistic at the same time. It can be understood as the error term at time t cannot be correlated with present, past, or future value of z, that is independent variable. So z cannot have any lagged effect on y. If we see if there is any lagged effect, then we need to use distributed lag model instead of the static model that we used here. Now we need to use distributed lag model, which can be shown as yt is equal to alpha naught plus beta naught z1t. Now there are lagged effect of z1, so another term would be z1t minus 1 and so on, plus error term. Under first three assumptions, we say that OLS estimators are unbiased, conditional on X. So mean value of beta can be estimated. Now there are three more assumptions in line, but the remaining three does not impact unbiasedness of OLS estimators. The fourth one in line is homoskedasticity. This assumption tells that error variance is constant across all time period. That is variance of u at time t condition on z is equal to a constant sigma square. Fifth assumption talks about no serial correlation. So what is serial correlation? It defines correlation between two error terms. So this assumption says that correlation between ut and us, where t and s are not equal, correlation between these two errors is equal to 0. Uh, if the errors are correlated, then we say that errors suffer from the problem of serial correlation. We'll talk about this problem later on in the session. So how does the fourth and fifth assumption help us? The first three gave expected value of beta, right? Under assumption 1 to 5, we get variance of beta, condition on Z. Now the last assumption talks about uh, normality assumption. So in this assumption, error terms are independent of Z, that is independent variable, and these error terms are also independently and identically distributed as normal with mean 0 and variance sigma square. So you see this assumption 6 in itself, it implies 3, 4, and 5. But it is stronger in the sense we are also talking about independence and normality assumption. So what is the use of this? Um, with we can say that under null hypothesis, each t statistic will have a t distribution, f stat will have a f distribution, and the usual construction of confidence interval that is also valid. So using these assumptions, we can figure out whether estimates are statistically significant or not. So in the nutshell, we get best OLS estimate if all these 6 assumptions are met. Now the problem is the strict exogeneity and the no serial correlation assumption. These are unrealistic in the practical world. For example, if there is any omitted variable in our model or if there is any measurement error, so these situation can cause error at time t to be correlated with explanatory variable. And so in that situation, zero conditional mean assumption cannot be met. Likewise, if there is any correlation between error term, which turns out to be a reasonable characterization in many time series applications, so there also the fifth assumption is not met. In those scenarios, we also have weaker version of these assumptions that makes OLS estimates consistent if not unbiased. We'll not go into details here. So just for example, if you're talking about zero conditional mean, this strict exogeneity assumption is changed to uh, exogenous in the contemporary times. So we can say that uh, mean of error term UT condition on uh, ZT, I mean, independent variable at time t is equal to 0. Now we are not talking about Z across all time period. So that's how we weaken the assumption. The consistent estimates that we get from the weaker assumptions are also asymptotically normally distributed. And the usual OLS standard error, T stat, F stat are also asymptotically valid. Yeah. So that was all about assumptions. The next topic in line is stationarity of time series. So this is a very important concept in time series. Um, how do we define a stationary process? We call a time series stationary if the probability distribution are stable over time. So as to say, a relation between dependent variable and independent variable, it doesn't change over time. We can understand this in a simple way. For example, if we allow this relation to change over time arbitrarily, then we cannot hope to learn how change in X can affect change in Y. How we cannot predict Y. Uh, there are many examples of stationary process and non-stationary process. For example, if there is any process with time trend, then definitely it's not a stationary. Now the next question is, how can we figure out which time process is stationary and which one is not, and how can we remedy for this problem? Is there any remedy? Can we make time stationary process or non-stationary processes as stationary? Yes, we can. First, let's look at the conditions required for stationarity. So the first one is a constant mean. the process should have a constant variance. And the third one is the covariance between explanatory variables at time t and time t plus h. So this covariance between, let's say, xt and xt plus h, it should depend only on the time distance h and not on t. Yeah. Some important points to note here is that stationarity condition doesn't say anything about correlation between xt and t plus 1 or xt plus h. It only they can be correlated, but then this covariance it should depend only on h and not on t. Let's see if we can see any time series process. Okay, so here is the time series process. We can see that the mean is somewhere around 0, but the variance is not constant, right? And there is more swing in the starting, and then it goes away. Another process, let's say constant variance. So there is not much swing. We can say it has a constant variance, but definitely this process doesn't seem to have a constant mean. Hence, these two processes are not stationary process. Another one, let's see. So this process seemed to be stationary, not much swing, and the mean is also around 0. Yeah. If you've heard about autoregressive and moving average processes, these are also stationary. Um, let's talk about these processes briefly. So the first one is autoregressive AR process. AR model, so as to say, it establishes that y at any time t is a linear combination of the previous realization plus some error. So in autoregressive process, if let's say we have yt, it will depend upon previous lags as yt minus 1 plus some error term will be there. Yeah. So here you can see I have shown AR1 process. Another process is moving average. We define moving average processes as, this can be said as correlated noise in the data. So the observed processes, it will depend upon previous process as well. Here I have shown moving average process. So xt is equal to et plus alpha 1 et minus 1. Here E is IID sequence, that is independent and identically distributed sequence, and X is called moving average of order 1. Why? Because there is just one lag of the error term. So these autoregressive and moving average processes are also stationary. How we can see it here, we will not go into the details, mathematical details, but here I've just written the formula. For autoregressive AR process of order 1, which can be shown as yt is equal to rho yt minus 1 plus error term. So there is just one lag, hence we call this process as AR1 process. If there are more lags like shown here, uh, there are two lags here, so this is AR2 process. Now the mean of yt is equal to rho to the power t times y naught. And the variance of y is written as variance of error term divided by 1 minus rho 1 squared. Covariance is also written, which is rho 1 to the power h times sigma y squared. So we can see if rho is less than 1, under the condition when rho is less than 1, mean will be equals to some constant less than y naught. Variance will be also equal to some constant 1 minus less than 1 will be a number smaller than 1, which will make sigma y square little bigger than sigma e square, but it will be a constant. Hence, we can see that AR1 process is a stationary process. Looking at covariance, we can see that sigma 1, this covariance depends only on H and not on T. Hence, all the conditions are met. Uh, there is another corollary to this formula shown here. Generally, writing sigma y square can be written as error variance sigma e square times we have a geometric progression here. So under the general condition, when rho is equal to 1, then this process is called as unit root. And in that situation, sigma y square will be equal to t times error variance. Hence, the variance of y is dependent on time under the condition when rho is equal to 1. Rho is this coefficient of yt minus 1. So under unit root, this process will explode. So we can see here it's moving slowly. Now, as time goes on, we have larger swings. Okay, so to summarize, we saw two processes here, autoregressive and moving average, and these two processes are stationary because all the conditions are met. Now, I'll come back to this segment later on. So the next question is, how do we test if a process is stationary? There are various methods, various standard tests to do that, and all these tests are inbuilt in statistical packages. If we work with R or Stata or Python, so we have all these already inbuilt in those softwares. So the first one is unit root test. We would need to deviate a little bit here to understand unit root, and I have just discussed unit root. Mathematically speaking, we say that any process, if it is written in terms of monomials, each monomial corresponds to a root, right? And if any of those root is equal to 1, then that is called a unit root. So here we saw if this coefficient of lagged term is equal to 1, then the process is said to possess a unit root, and in that situation, the process simply explodes. Yeah. Now, how do we use that unit root in testing for stationarity? If any process has unit root, then definitely it is not a stationary. So Dickey-Fuller test make use of the same, and then we can see it here. For example, again, I have taken one autoregressive process here. So if yt is a constant plus rho times t minus 1 plus some error term, we can write this equation in terms of delta yt. All we have done is subtracted yt minus 1 from yt. So this delta yt now becomes mu plus delta yt minus 1 plus some error term. We test in Dickey-Fuller under null hypothesis, we test if this delta is equal to 0. Now when delta will be equal to 0, rho will be equal to 1 because delta is equal to rho minus 1. And if we reject null hypothesis, in that situation, delta is not equal to 0, right? And rho will not be equal to 1, right? So if we reject a null hypothesis, then there is no unit root present. So that's how we test for stationarity. There are a few more tests. So the next question is, now we have understood how to check for stationarity. Is there any way we can convert non-stationary process to stationary? Yes, we can. And there are certain methods to do that. The most used one is the differencing method. So we take the first differentiation of the process, and that's how the process is converted from being a non-stationary to a stationary process. For example, if a process looks like this, on taking the first differentiation, it converts to this. Yeah. There are other methods as well. We can take a log, or we can take an root, or a combination of any of the above to make non-stationary to a stationary process. Uh, there are certain time series processes with deterministic trends. Any trend make time series non-stationary. So how we can make those stationary? We can simply uh, add a time trend T in the model to detrend that process. Uh, if there is any seasonality in any time series process, all we need to do is to add dummy variables to capture that seasonal effect in the time series process. We call these trends and seasonal time series process as a spurious regression problem. Um, these problem occurs, when time series is non-stationary and also independent at the same time. We have not covered in detail about independence and weakly dependence of time series, but just to summarize, we can say that use of stationarity, it simplifies the law of large number and also the central limit theorem. While weakly dependence criteria, it replaces the assumption of random sampling. It implies that if a process is weakly dependent, then law of large number and central limit theorem holds true. So weakly dependence and stationarity of the processes are criteria that we can use to model. Yeah. Okay. Moving on, let's talk about few models. We have discussed briefly about autoregressive model and moving average model. Here we see a combination of these two. So the first one is autoregressive moving average model, ARMA, PQ, where P denotes order of AR term and Q denotes order of MA term. Another one is ARIMA, ARIMA, autoregressive integrated moving average. This is defined by P, D, and Q. So first of all, what is the difference between ARMA and ARIMA model? So these are the class of model that explains time series based on its own lag and lagged forecasted error. The only thing that sets these two models apart is the letter I. So ARMA model is used in stationary processes. But if the process is not stationary, then we need to use ARIMA model. And the letter I, the characteristic D is the number of differencing required to make the time series stationary. Um, because we are not going into details, I'm just summarizing all the models here. The next question is, how do we find the values for P, D, and Q? For this, we can use ACF and PACF plot. ACF plot is the autocorrelation function plot, and PACF is partial autocorrelation function. Essentially, these are the plots of autocorrelation of a time series by lag. Um, mm, when we're looking at correlation, uh, so correlation can be caused because of, there can be a direct correlation, there can be an indirect correlation as well. So ACF plots, it looks into both direct and indirect correlation, while the PACF plot, it seeks to remove indirect correlation, presents just the direct ones. Yeah. Uh, Now let's say we are trying to find order of autoregressive model AR. Okay, so in that case, we should inspect PACF plot. Why? Because for AR process, ACF is really strong until a certain lag K, but then because of inertia, it is carried over to subsequent lags as well, and then it slowly trails off at some point, while the PACF plot declines sharply after K. So in order to find autoregressive lag, we should inspect PACF plot. Likewise, for moving average order, we should inspect ACF plot. Here, the situation is vice versa of the previous one. For moving averages, what happens is um, it's the opposite of AR. So for moving average, PACF plot is really strong until a certain point, but then it is carried forward because of inertia to subsequent lag, and then it slowly trails off. While for moving average, ACF plot declines sharply after K. So this is just to summarize. I will try to take these plots, ACF and PACF plots in detail in some other session. Okay, so far we have seen few models. Now in the next section, we will look at the problem of heteroskedasticity. This problem occurs when error variance changes over time. Right. Um, So what happens when error variance changes over time? We have seen earlier that uh, T stats and F stats and usual statistics no longer remain valid. So what do we do? First of all, how do we test it? So we can test heteroskedasticity using white test or BP test. And as a remedy of the problem, we can use robust standard error, right? There is another concept called dynamic heteroskedasticity. This is time varying variance, which depends upon lagged effect. So there is time varying variance in the problem of heteroskedasticity, but then that variance depends upon lagged effect. That is autocorrelation, right? Um, if we want to, mm, for example, let's talk about any pricing model. So this arch, autoregressive conditional heteroskedasticity, uh, essentially what will happen, if there is a huge volatility in the pricing model, then we would like to model expected return as well as we would like to take care of the risk. So we can do that using arch model. Few points to note. Uh, this arch process does not impact consistency of OLS. We would not have an unbiased estimate. Rather, we would have a consistent estimate. Uh, but then the T statistic, as I said earlier, those will be asymptotically valid. GARCH, which is generalized autoregressive conditional heteroskedasticity, is a extended version of ARCH where we also include moving averages process with AR, along with AR. Yeah. GARCH PQ model is equivalent to ARCH-Q model if P is equal to 0. And in case P and Q is both equal to 0, then we are left with white noise. What is white noise? White noise is something which cannot be predicted. It is pure noise. So if we talk about any signal that consists of two component. The first component is something that can be predicted, and that's what we model. And then there is another component which cannot be predicted. So this pure noise is called as white noise. arch Q model looks like this. Uh, Simply speaking, for example, let's say if there is any arch process written as, yt is equal to c plus error term. Now here in this case, a variance of this error term, let's say sigma t square is equal to ht, because now this is no longer constant. Rather, this variance is dependent upon, it has a lagged effect. It depends upon error of the previous term. So sigma t square is written as beta naught, b naught plus b1 ut minus 1 squared. Remember the stability condition from the AR process we discussed earlier. This coefficient b1 has to be less than 1. If it is equal to 1, then the process simply explodes. In general, this ht can be written as b naught plus b1 ut minus square plus b2 ut minus 2 square, so on and so forth, in order to include more lagged error terms. So that will be arch Q model. The last topic we are covering today is autocorrelation. So the first question is, what is autocorrelation? We have discussed it briefly earlier. When errors are correlated across time, we say that the process is suffering with serial correlation. For example, how do we interpret correlated errors? For example, if there is an interest rate that is abnormally high for current period, then it is likely to be, abnormally high in future periods as well. How can we test for autocorrelation? Again, there are some inbuilt tests. The first one is simple. We can look at the lag plot called as correlogram. Then we can use Durbin-Watson test. This test is used under strict exogeneity assumption. Then there is Breuisch-Gottfried test. Sorry if I'm not able to pronounce the name correctly. These are all inbuilt tests in various statistical packages which can be used. Let's see how we can fix the problem of serial correlation or autocorrelation. So for the process, there are certain steps. As a first step, we run OLS regression of YT on all the independent variables, x1, x2 until xt, and then get the OLS residual for all time period. Now, as a next step, we would run U error at time t, that is UT, on lagged error term for all time periods, right? And then obtain the coefficient, let's say sigma on this UT minus 1. So if we say, if this is the error term, then we would like to obtain the coefficient on UT minus 1. And then use the normal t statistic. Under null hypothesis, we say that coefficient on lagged error term is equal to 0. As an alternate, we say that that is not equal to 0. If H naught is rejected, then there is problem of serial correlation. How do we fix the problem? We can use feasible GLS procedure. Again, these are all inbuilt procedures. This procedure is used under strictly exogenous assumption. If that assumption is not met, then we can compute serial correlation robust standard error provided by Newey West. Again, this is inbuilt in the package. So any statistical packages. So we can use that to fix the problem of serial correlation. Um, While the first, if we talk about the first method, their t statistic will be valid in the scenario when non-strictly exogenous regressors are present. In that scenario, we can use LM or F test for higher order correlations. So that's all for today. I'll try to explain some complicated concepts from time series. I'll try to include error correction model and other concepts in some uh, other session. That's all for now. Thank you so much.